We're solving problem 23 from the 2021 F equals ma. An imperfect spring has a restoring force F that depends on displacement x from equilibrium as in the graph shown below. The slope of the curve for x is greater than negative d and x is less than d is a constant negative k. A mass m is attached to the spring and released from rest at position x equals a, where a is greater than d. What is the period of subsequent motion? So for this problem, since we're dealing with all of the springs, since in a mass spring system, we know that we can say that T0 is equal to 2 pi times m over k, the spring constant. Since it's a constant, we want simple harmonic motion, so we solve for simple harmonic motion in this case. So 1/2 mv squared is equal to 1/2 k a squared. But what is our a in this case? Well, so the second sentence, a mass m is attached to the spring and released from rest at the position x is a, where a is greater than d. Basically, this just means that we want to do a minus d squared. And then the 1/2s can cancel out. And then we end up with v is equal to a minus d times the square root of k over m. Why do we want an expression for v then? We want to solve for v because the velocity ties into the equations for time. So basically, since we want to find the period of the motion, we just want to sum up the times. We already have one, we just need to solve for the other, the current time. Since it's happens 2 times, you have to multiply the equation for time by 2 and then add it to that later on. So our equation for time in this case would be t is 2d over v, which we solved for. That's why we did it. Which is 2d over a minus d times square root m over k. So now we have the two equations for t. Our total sum of the time is going to be t0 plus 2t because it does it 2 times. This is going to be, we can factor out an m, square root m over k for both. And then since you multiply this by 2, well, this is just, to is going to be a 2 pi. And then you're going to have to add this multiplied by 2, so 4d over a minus d. This is going to be our answer for this problem, and we are simply just done.